So yesterday we basically got up to introducing DFT with the caveat that we didn't really go through all of the all of the parts of the Hamiltonian. So given that today we're going to do some practical examples a little later, I think it might be worth repeating a few of the things from yesterday. Not too much, but a little bit. So I'll start from the beginning, but I'll go fast through the slides that we already looked at yesterday. Right. So what we effectively said was that in order to solve the many-body Schrödinger equation, we would firstly, at a bare minimum, have to be able to write down the many-body wave function. But in order to write down the many-body wave function, and by write down I mean store on a computer, we would have to be able to store a discretized n-body or 3n-body object, 3n dimension object. Okay, so what we said was that if we were going to, where's the chalk gone? Yeah. If we were going to, for example, take linear space and divide it into 10, so we had 10 discretizations from start to finish, and we did that along every dimension. So there's 3 dimensions, and then we were to, for example, go to 4 dimensions, then we would have 3 dimensions times 10, so 10 times 10 times 10 times 10 in the 4th dimension, and then we'd have to do that in 3n times. So we would have our discretization density times 3n, okay, and that would end up, well, obviously a very, very large number for even quite small numbers of dimensions, numbers of particles, because n is effectively the number of electrons in our system. Right, so even to store a wave function of 2 electrons, 3 electrons, 4 electrons, we need more storage space than we have available. Right, so we have this exponential growth of the wave function, we have inter-particle difficulties, and we have these very high dimensioned integrals. Okay, so this leads us to not want to solve the many-body Schrödinger equation, or we do want to, but we can't because it's impossible. So we led to isomorphisms of quantum chemistry. So isomorphisms are reformulations of the Schrödinger equation of quantum chemistry, which is exact, but sidesteps or avoids needing to store the many-body wave function. And the one we are focusing on is DFT, although there are others. We will speak by necessity about the Hartree-Fock method, and depending on time, we might talk about quantum Monte Carlo. In the schedule, in the syllabus, we are supposed to have a couple of sessions about stochastic methods. So that would almost certainly be about quantum Monte Carlo, but it all depends on time and probably on people's interest. All right, so this is where we got to yesterday, basically introducing DFT. And what we really need to understand, we'll go past the background. What we really need to understand is that DFT is an exact reformulation of quantum mechanics, right? So the Holmberg-Kohn theorems state that firstly, everything that we need to know about the ground state of the system, So all the ground state properties of the system are encapsulated, are uniquely determined by the electron density of the ground state. Okay. So this is quite similar to what we said in quantum mechanics about in Hilbert spaces and the state vectors. So we said every conceivable piece of information about the quantum system is contained within the state vector. Well, the Holmberg-Kohn theorem, the first Holmberg-Kohn theorem, effectively states that actually, alternatively, all of the information about the ground state, not about every state, is contained within the density. Okay, and then the second theorem basically introduces the variational principle, which means that if we want to find the ground state energy of the system, we have a functional, which is a function which takes a function as an argument, and if we feed that universal functional with a density, a guess for the density, we will get an energy out. Okay, so what we said yesterday was if we want the energy of the system, it will be that universal functional of the system. It will take it a density. That density is a guess to begin with, but as we change that density, the energy will change. And so if we change the density and the energy goes down, then we know we must be going towards the ground state. Because the ground state has the lowest energy of any system. So as we change the density, we change the energy. If we change the density and the energy goes down, we're going in the right direction. So this is a good direction. We go that way. And then we change it again. It's gone up. Not going that way. Try again. Goes down. Once the energy stops going down, then we know we've reached the ground state. Okay, so effectively, guess goes down, guess goes down, guess goes up. Nope. Try again. Goes down. We're going towards the ground state, the lowest energy. Right. So we're not going to repeat all of this from yesterday, but we will say something about the variational principle. So that's that. As we push our density towards the ground state, we push our energy towards the ground state. But we can also take the derivative of this functional, the functional derivative, and we can, rather than just guessing the density and trying to find a new density which makes our energy lower until we run out of search directions, we can use the gradient or the derivative, functional derivative, as a search direction. Okay? So this gives us all of the kind of high-level knowledge we need in order to apply DFT, but the big problem is that we don't know the form for some of these parts of the functional. Okay? So we've already said we've already said that that we know the form for the Coulombic parts, the mean field electrostatic parts of the functional. So by that I mean what's called J here and what's called V external. So V external is just an integral with the density. Did we write density like that? Yes. So the density and, excuse me, and V, well, I think I've probably written it on the next page. It's probably easier just to yeah. Right. So right. So if we want to assume that that we're using a non plane wave basis, okay, We'll come back to plane wave basis. If we've just got some atoms, what we're assuming is that our V external is the nuclear potential of those atoms, right? J, we're assuming, is the mean field electrostatic potential. I'm going to call it VH, but it could also be called J, right? And so what we're going to write for that is just that we've got a density something like that, right? So those two parts we can write in terms of the density, okay? But the kinetic energy, we don't have a form in terms of the density, okay? So there's approximations, but there's no exact kinetic energy expression in terms of the density, okay? However, because of the Kohn-Sham approach, whereby they said, well, okay, we don't have the form for these parts of the functional, like the kinetic energy. We don't have a form. But what happens, because all we're really trying to do is to find the density of the system, what happens if we made another system which resembles our original many-body system in some way, but is easier to calculate, and we know the form of some of these expressions. And so what they effectively said was, if we have a system of some atoms, and it has some density, electron density around it, and this is the so-called the many-body density, okay? What we're asking is, if that's our many-body density, can we write this density, can we write a density which is the same as that density, it has the same form, but is actually composed of non-interacting pieces, right? So can we take a system of non-interacting particles, right, which has the same density as this, okay? So they have the same density. Right. So what that really means is that now we're going back to the way Hartree-Fock calculates things like kinetic energy. We have a bunch of orbitals, okay? So we have a bunch of orbitals in state space, except these are single particle orbitals, right? So we've got an index over the particles, and so every electron has one set of orbitals in three dimensions, okay? Unlike the many-body wave function, which has 3n dimensions, okay? So that we can't represent, but we can represent n times 3D wave functions, okay? And then what we're trying to find is, well, let's just say that we're trying to find a non-interacting density, so that the particles are non-interacting. The density is supposed to be the same as our many-body density, okay? Because what that allows us to do then is, if our system is made up of these non-interacting orbitals or states, then we can calculate our kinetic energy quite simply as the sum over the kinetic energy of each of our non-interacting orbitals. So density's quite easy to handle. Density is quite easy to handle, and kinetic energy becomes, if these are our orbitals, kinetic energy is just going to be one of our states. So in this case, we've taken psi, but I'll use phi. like that, and I've got an index on it. And so what we're doing is that we're applying an operator to it, right? So a second derivative operator on that state just gives us another state, right? So we can call it, oh, I don't know, prime I. Okay, so we just get a vector. So we have an operator, which is a matrix, okay, in a certain basis. That operator is applied to the state, which is a vector. And so matrix operator times vector gives us another vector, okay? And so then we've got vector multiplied by conjugate vector integrated over space. What we're effectively doing now is we're taking our other vector, right, which is conjugated. So we have our Dirac notation the other way around. And we're we're dot producting that vector with the derivative vector. And we're summing over I. And this gives us our kinetic energy. Okay? So effectively, all we need to do in this case is a derivative. Okay, so we just do a derivative twice on this vector. We need to be able to pointwise multiply a vector by another vector. Okay, so every point in our vector we need to be able to multiply by the other vector. So by point I mean point in space. At this point on a vector and this point on another vector, we need to be able to multiply the value at that point. And so what we have here is the multiplication of that derivative vector with the conjugate of itself. And then we need to be able to integrate over space. These are easy operations, right? These are things you can do on a computer with no difficulty. Okay? And using these this basis, this set of states, what we can do is we can go back to the density, and then we can calculate. We can also calculate all of the density-dependent terms that we could already calculate in a Hohenberg cone. Okay, so Hohenberg cone is a nice idea, but in practice, because there's no obvious way to calculate the kinetic energy, it's useless. Okay, you will hear a Hohenberg cone DFT called orbital free DFT. Okay, and it does exist. People do it. There are codes that can handle orbital free DFT, but it's not accurate, except under some very, very limited conditions. Cone sham DFT is what most people are referring to when they say DFT. Okay, so if somebody says I've done some calculations in, for example, Castet, VASP, Quantum Espresso, Gaussian, NW Chem, any of the common DFT packages, they're doing cone sham DFT. Okay, it's only if they say I'm doing orbital free DFT that they're doing something a little bit more esoteric. Right, so if we can calculate the density in that way, we can feed the density into the density-dependent terms like the external potential, the external potential energy we would need the density for. The Hartree potential and the exchange correlation term. All right, so I think this is pretty much where we got to yesterday. Okay, so just a brief recap today, and now we will continue. Right. So at this point, what we have is a set of equations, coupled equations, which looks awfully similar to the Schrödinger equation. Okay. The only difference between this, or at least the only difference that you can read on the board, is the fact that we have a state index compared with the Schrödinger equation. Okay. In the Schrödinger equation, because if we had more than one particle, the many-body Schrödinger equation would have 3 dimensions for every particle. The state index would be encapsulated in the dimensionality of the wave function. Okay, so Schrödinger equation has a wave function, a many-body wave function. Cone-Sham equations have wave functions. Okay, there's more than one of them. Right? So just want to drive that home. So if we have many-body Schrodinger equation, we have 3 n dimensions. Okay? If we have Cohen-Sham equations, we have n 3 dimensions. Okay? All right? This is a different thing. All right? All right, so what are we doing here? What are we doing here? So effectively, what we have to handle, excuse me. What we have to handle is a set of coupled eigenvalue equations. All right? Do we have actually? No, we don't. Okay. So for instance, if I have a Hamiltonian operator, right? If I have a Hamiltonian operator, and we know that our Hamiltonian operator is a second derivative term plus our Cohen-Sham effective potential, right? And we want to apply that to a bunch of states. Okay, and so we're effectively getting our Hamiltonian matrix by doing this. Okay, our Hamiltonian matrix, Hij, is now going to be equal to something like this, where we have H11, H12, H21, etc. And this is an n by n matrix, square matrix. Okay, n by n square matrix. So in order to solve this, what we're actually going to have to do is diagonalize or take the eigenvalues of this matrix. Okay, so if we write our Hamiltonian matrix, all right, so this is going to be a matrix. If we write this as an eigenvalue multiplied by a set of vectors, so I'm just going to call them V, V conjugate transpose, and we've got a set of, so we'll also maybe, okay, so we've got a set of vectors multiplied by a matrix of, a diagonal matrix of eigenvalues, okay? If we can get that diagonal matrix of eigenvalues, all right, all we have to do, at least in the orthogonal case, is to sum the eigenvalues, okay? So if we take the trace of the eigenvalue matrix, which is just the sum of the eigenvalues, okay, this is the energy of the total energy of our system, at least the band structure energy of our system, okay? So effectively, it's quite easy to calculate the energy with a set of coupled non-interacting particles. It's much easier than having to do many body work. Right. So what's the implications of having an isomorphism like this? It's really that it enables us to calculate or make predictions of molecular interactions, crystalline properties, basically atomic physics and chemistry accurately in a way which wasn't possible before for system sizes which are not feasible for other quantum chemistry methods, like even Hartree-Fock. Okay, it forms a basis for a lot of the computational approaches that are bandied about in quantum chemistry and solid-state physics. Not everything, but it's a kind of a cornerstone of computational work. Why? Because it's a balance. It's a balance between computational accuracy and speed. It doesn't get either perfectly, but it does well enough. It's okay. Right, but what we have to now contend with, which is the last thing to deal with, is the final term in the Hamiltonian. Okay, so what we've avoided mentioning is that we can calculate the energy of the system, we can calculate the kinetic energy of the system, we can calculate the mean field electrostatic interaction between electrons, we can calculate the electrostatic interaction between electrons and nuclei, but we can only do that at the moment with a Hamiltonian like that, okay? And so if our Hamiltonian doesn't have that part, what we're actually calculating is called the Hartree approximation, okay? So the Hamiltonian without that part is the Hartree approximation. Not Hartree-Fock, Hartree, okay? And Hartree-Fock is not accurate enough for most calculations that we want to do today. Hartree is even worse, okay? So what that part is, the exchange correlation, in DFT can be thought of as the error between Hartree and the correct answer, okay? In Hartree-Fock, because we have an extra term, which is the exchange energy, okay, in Hartree-Fock, the correlation is defined to be the difference between Hartree-Fock and the real answer and reality, okay? All right. So I don't know whether it's worth writing it down, but maybe not. So in Hartree-Fock, the exchange term is calculated exactly, okay? So this is a consequence of Pauli exclusion, the Pauli exclusion principle, okay? So electrons are fermions. They have half-integer spin, okay? So the statistics for half-integer non-distinguishable particles means that whenever we exchange the index of a particle with another particle, let's write it down in a many-body wave function, right? So if we say our wave function has index, I don't know, R1, Ri, Rj, Rn, okay, this is a many-body wave function. If we were to exchange the index I and j, right? If we were to swap I and j, our many-body wave function gains a negative sign, right? So if we switch the index of particles, what we get is a negative sign. Our wave function is anti-symmetric, okay? And so in order to encapsulate that and to get the right answer in our calculations, we need an exchange energy, and that encapsulates this property of fermions, but it encapsulates that property of fermions in order that we effectively reproduce Pauli exclusion of fermions in our calculation. Okay, so it's a roundabout way of getting Pauli exclusion in our calculations. And so if we had a Hamiltonian which has all of the terms up to exchange, okay, then what we're effectively doing is Hartree-Fock, okay, and then correlation, the correlation part, is the difference between Hartree-Fock and the real answer, and the real many-body quantum mechanics that we want to calculate. Okay, so in Hartree-Fock, correlation is just the error, and we don't calculate it. In DFT, we have an approximation for correlation, but we also have an exchange approximation. So this is the difference between Hartree-Fock and DFT. Hartree-Fock has exact exchange. Most DFT, or at least semi-local DFT, has an approximation for exchange. So you could say it's worse than Hartree-Fock, but it's not worse, it's better, because we also have an approximation for correlation. Okay? All right. So how do we approximate those things? At the most basic level, we use the local density approximation. Okay, the local density approximation. Now, I was looking through some slides. Yes. So in another lecture course that I did, I made some other slides. Okay. In my other slides, I put pictures in them. So for this course, I was thinking I would just draw everything on the board. But I was thinking maybe I'll just go back to one of my other lecture slides here, because I think the picture is maybe clearer than what I'm able to draw on the board myself. Okay, so if we were to say that the density of our system, as we calculated it, I keep rubbing it off the board, but our density is that, something like that, okay? And that is our density, okay? So if we plot it in 3D space, our density, and we divide space into a grid pattern, and we take a piece of we look at one point on the grid, okay? That density has one value, right? It has a scalar density value, right? Electronic density. And so what we can do is we can construct a homogeneous electron gas, which is an electron gas with that density everywhere. Okay? So homogeneous electron gas with a high density, homogeneous electron gas with a low density, homogeneous electron gas with an intermediate medium density. Okay, so we can construct a homogeneous electron gas with any density we want. And so what we do is for every point in our density, in our real density, we construct a homogeneous electron gas with that density. Okay? And then that allows you to derive an equation for the homogeneous electron gas, for the exchange of the homogeneous electron gas, which looks a bit like this, right? Ooh, it looks exactly like that. Okay, so actually all we have to do in order to calculate our exchange under the LDA, which is just doing that, right? So we have two options. We can either take every point in our space, calculate a homogeneous electron gas with exactly that density, and then take this system and calculate the exchange and the correlation, and then sum over all of these homogeneous electron gases that we've calculated for every point in our density. Or we can just derive the equations for the LDA for a homogeneous electron gas over the whole density. Okay? So we can do everything in one go with these two equations. Okay? We just feed in our density, raise it to the 4/3 power, and integrate over space, constant in front. That's our exchange energy. And then we've got a similar expression for the correlation. Okay? You might ask, how do we arrive at those equations? How do you derive them? Well, if we have time, we'll talk about that later. But effectively, to get the exchange, all you do is you say, I have a homogeneous electron gas, and I'm going to represent that homogeneous electron gas in terms of, say, a plane wave basis. Okay? So how do you represent constant with a plane wave basis? You just need to Fourier transform a constant. Okay? Fourier transform a constant. And if you take that Fourier transformed constant as your basis, and you put it through the Hartree-Fock exchange term, you will derive that expression at the top. Okay? And I put that in the notes, how to get from one step to the next, but we can talk about it later. For correlation, because correlation is defined as the difference between Hartree-Fock and reality, in order to arrive at the correlation for anything, you need more than Hartree-Fock. Okay? So the reason this term has a logarithm in it, in the correlation is because this comes from RPA, right? And so RPA is one way of going beyond Hartree-Fock. Okay, it allows us to look at plasmons. Okay, effectively how it is one way of looking at part of the correlation. Okay, so if we apply RPA, to the homogeneous electron gas, what we get is one way of calculating the LDA correlation. Okay, we'll talk about that in detail later, or maybe tomorrow. All I want to say is that this is the easiest way to get a correlation, to get an exchange and correlation term that we can put into DFT, which is not completely terrible. All right? Where's the other slides gone? Right. So once we've got that expression for the exchange correlation energies, or exchange correlation potentials, really, all we've got to do is integrate over space to get our exchange correlation energies. Right. We also need potentials. So in our Hamiltonian, the potential that we feed into our DFT Hamiltonian is the Hamiltonian has a potential term, right? The Condensed potential. And of course, the last term in the potential is the exchange correlation potential. So what we've got from exchange and correlation in the LDA, under the LDA, is an exchange correlation energy. Okay, so the question is, how do you get an exchange correlation potential? And you have to do it numerically, really. Okay, so effectively, all you do is take a numerical derivative of the exchange correlation energy with respect to the density. Okay, so there isn't a so you might think, all right, I can see that there's an exchange correlation energy here. I can see how that factors into my DFT calculation, and I have an energy contribution from exchange and correlation. But in order to apply that in the Condensed Hamiltonian, I need a potential. Well, there is no problem with that. It's just that we have to calculate it numerically, and then we get a potential over space, a scalar field. All right. So it's worth speaking briefly about what LDA is good for and what it's not good for. So most calculations you do, particularly in chemistry, are not LDA calculations. Okay? In chemistry, if you're doing calculations of organic chemistry or I don't know, biochemistry, they're almost always hybrid calculations, not LDA. LDA is considered to be garbage. On the other hand, in physics, what you find is a lot of people, even today, still run LDA calculations. So why are people in physics, physicists, happier with LDA? The reason is because they're running different kinds of calculations. Okay, typically in most physics, you're dealing with solid state, often metallic systems. Okay, quite different to the kind of things you're dealing with in chemistry. The upshot of running solid state metallic calculations is that your density is changing or varying slowly across space. Okay, so if you have running out of space, if you have a density in a molecule, if you have a density in a molecule, what you find is you often have, density which varies a lot in space. Right? So you might have high density, high density over a very short period of space. Okay. Whereas if you're dealing with a solid state periodic crystal of a metal, usually the density varies continuously and gradually in space. Okay? And this is the reason why LDA works better in those cases, because effectively LDA is like taking the exchange correlation energy that we don't know and asking the question, okay, if I don't know it, could I power expand it? Could I take the Taylor expansion of that thing I don't know? And the answer is yes. The first term of that Taylor expansion is the LDA. Okay. So if you take the Taylor expansion and truncate after the first term, the gradient term, what you expect from basic mathematics is that your approximation to the function will be poor if your function varies fast. Okay? If you have a slowly varying term, maybe the first term is good enough in the power expansion. Okay? However, the first term isn't good enough in a lot of cases. And for that, you need another term in the power expansion, in the Taylor expansion. Okay? And so this is known as the GGA, or generalized gradient approximation. Why is it not just a gradient approximation? The reason is subtle, but really it comes down to a bunch of caveats about how you calculate these things. If I simply take the gradient, what we'll find is that my energy will go discontinuous under certain circumstances. Generalized gradient means that in the places where the places where my exchange correlation functional goes singular, I'll just clamp it to 0. Okay, it's a very inelegant solution to the problem of a non-continuous function, but it works. Right. Okay, so what you can see on a high level, this is not the actual expression of a GGA, but it's the sort of high level expression of what's needed to be able to calculate a GGA. What do you want to call it? The energy density, right? It doesn't just include the density, the electron density, but also the derivative of the electron density. So it is effectively the next term in the Taylor expansion, the next term in the power expansion. Okay, and we can play this trick as high as you want to go. So the next step after GGA is the meta GGA, which involves second derivative information. And if we include second derivative information, we probably get a better result. But what we have to remember is that these things are not just 1D functions, but they have several dimensions, several parameters. So the more dimensions you include in this function, the more terms you include, the more parameters you have. Okay, so if you think about LDA, you have basically maybe one, maybe 2 parameters to completely define an LDA functional. In a GGA functional, you maybe need 3 or 4 parameters. Once you get to a meta GGA functional, you need 27 parameters. So the reason why meta GGA functionals have only recently been available is because it's taken this long to parameterize all of the parameters in the meta GGA. So, and there's 2 ways of doing the parameterization. So if you look at groups from chemistry, like Donald Truelaw, for example, what they do is they fit those parameters in the meta-GGA to a bunch of data. So you can take, for example, a whole load of calculations with a high-level code. For instance, you could be doing, I don't know, coupled cluster calculations, or in physics, something like GW theory, and you get some results for a whole load of different systems, and then you just fit a functional to that data. Okay, that's one approach. But the problem with fitting is that you can overfit, and you can find that if you don't fit a system which you're interested in later, you may find that your functional does not match that system very well. So the other approach, which is kind of the Purdue approach instead, there's two big guys in the US who are working on this kind of thing. The Purdue approach is more to derive mathematically or physically each of the parameters, and that's taken a very long time in a meta-GGA when there's about 27 parameters to derive. Okay. Right. So we'll talk about plane waves when we come back. Let's have a quick break.